Welcome to Impulse and Momentum. Momentum is the resistance to change in an object's motion. So back when we were studying Newton's three laws, his first law is known as the law of inertia. And we talked about as inertia as resistance to change in motion. In that case, we were mostly talking about something's mass. Something with a lot of mass has a lot of inertia. And something that's very small, not a lot of mass, is easy to move around, so it doesn't have a lot of inertia. We're going to kind of expand on that. The idea of momentum contains both that piece where things that have a lot of mass are difficult to change their motion, but also things with a lot of velocity. Their motion is difficult to change as well. So momentum combines those two ideas. We can calculate the momentum of an object using the following formula. P equals mv, where P is momentum. Isn't that fun? P for momentum. Spelling means nothing to physicists, I guess. This is momentum. And that's, we're going to talk about the units of that in a second. This here is mass. That's in kilograms. And this part is velocity. And that is in meters per second. So if we do a unit comparison over here, we're taking kilograms and multiplying it by meters per second. And so it would follow that the units of momentum are kilogram meters per second. Or kilograms times meters per second, however you want to put it. Often we find that kind of compound units like this have a named unit that goes with them, like force is kilogram meters per second squared, and it's named newtons. This one doesn't have one. We just have to call it kilogram meters per second. Okay, so that's the formula for momentum. Now, if you want to see an illustration of momentum in practice, you should just go to YouTube and search up Jerome Bettis. If you don't know who that is, he was a football player when I was growing up. He was a running back for the Pittsburgh Steelers. Quite a large human being. Usually running backs aren't that big. This man was abnormally large and abnormally fast. So he was difficult to get his motion to change. Anyway, it's fun to watch. Check it out. So that's momentum. Mass times velocity. So it's a pretty simple concept to put together. Impulse, I, is the average force and time needed to change the momentum of an object. Okay, so that's a little bit difficult to grasp, I think, at first. But if we think about it as the change in momentum of an object, that works a little bit better. So however momentum is changing, that's the impulse of an object. So if we're trying to stop something moving really fast, if you calculate the momentum of the object and what change it would take to bring it down to zero, that would also be the impulse of the object. Okay, but we can calculate it a couple different ways. So our first version of impulse is going to be I equals F times change in t. So let's think about this for a second. You're standing in front of a train and you need to slow it down to save the damsel in distress who's tied to the tracks, you know, Superman thing going on. In order to stop the train, you would need to exert a certain amount of force on it, but it wouldn't be enough to just push it once for a moment. You'd have to push it with a certain amount of force over a certain amount of time, and as long as you were able to keep pushing for enough time, you could slow down that train to zero. Okay, and so what this is saying is that in order to change the momentum of an object, you need to exert a certain amount of force for a certain amount of time. Okay, so this is impulse. This F here is force, and this T is time. Time is in seconds, force is in newtons, and impulse is then in newtons times seconds. Impulse is in newton seconds. For some reason, that doesn't seem like a real unit. You could modify that a little bit, though. So if we look at newton seconds as its own unit, newtons times seconds, remember that newtons is actually a compound unit. It's kilogram meters per second squared. Okay? And if we take that, kilogram meters per second squared, and multiply it by seconds, what happens is this squared goes away. That's squared right there. We're just canceling out one of the s's, one of the seconds. So you end up with, instead, kilogram meters per second. That's familiar from somewhere. Oh yes, right here. Momentum is measured in kilogram meters per second. And so impulse is force times time, but it's also equal to the change in momentum of an object. Okay, and that's why its units are the same as momentum, because when you're calculating change in momentum, you should get the units of momentum on the other side. Okay, these things, impulse and force, are both vectors, so they should have an arrow on top here, because they both have direction. The impulse will match whatever direction the force is. So if you're pushing north on the train, the impulse is going to be north. Okay, you're changing the momentum toward the north. When a net force acts on an object, the impulse of the net force is equal to the change in momentum of the object. That's exactly what we just said, just in a more formal way. Impulse is equal to change in momentum. So here's what we're saying. I equals change in P. When a net force acts on an object, the impulse of the net force is equal to the change in momentum of the object. So that's what we just said, that impulse is equal to change in momentum. It's just said in a bit more formal way as a theorem. So here's what we're saying algebraically. Impulse equals change in momentum. That's a pitiful triangle, but sure. Impulse equals change in momentum. Both of these things are vectors. Okay, this impulse is equal to force times change in time, and it's equal to change in momentum. Okay, so that's final momentum minus initial momentum, right? Change is just final minus initial anything. So if we're putting in the formulas for both of these things, you're going to go m2 v2 minus m1 v1. So this is final momentum, I should put arrows on these things, and initial momentum. So you're just subtracting the momentums to get change in momentum. Usually, M1 is equal to M2 because you're talking about one object whose mass probably isn't going to change while you're changing its motion. Probably while you're tackling Jerome Bettis, you're not also cutting off his arm. So usually the starting mass is equal to the ending mass. There are a few situations where it changes, like say you're a cowboy riding a horse and you and the horse together have a certain momentum, but what happens if you jump off the horse? Then the mass has changed, right? Then you're two separate objects. Okay, so then we can usually, in most situations, say force times change in time is equal to common mass times the change in velocity, v2 minus v1. Okay, so this force times change in time equals change in velocity. This is always true, regardless of whether mass is changing or not. This is true in almost every circumstance because you're most often not going to find that mass changes. Okay. Sometimes mass changes, and so you can change the algebra as needed. We're going to do a couple examples here. A baseball with a mass of 0.15 kilograms has a velocity of 38 meters per second west as it approaches a batter. The bat applies a force, causing the ball to move at 58 meters per second east. So the baseball had momentum going toward the batter, and then the bat contacts the baseball and completely switches the direction of the momentum and sends it back the other way. So we can figure out the impulse acting on the ball by the bat because there's a change in momentum. Okay, it doesn't tell us anything about the force and time required to do that, so we're going to have to use the impulse momentum theorem, that I equals mass times V2 minus V1. Okay, I used the common mass formula because the mass of this baseball isn't going to change. Okay, so this is totally valid for this situation. So I, because we're looking for the impulse, is equal to 0.15 kilograms times V2 is 58 meters per second minus V1 is 38 meters per second, but these have different directions to them. So I'm going to say that east is positive and west is negative. You can switch it around if you want, but that means you'd have to put a negative on the 58. So we're subtracting V1. V1 is negative 38 meters per second. Okay, so this is V2, 58 meters per second east, minus V1, which is 38 meters per second west. And when we do that whole calculation, we should end up with an impulse of 14.4 Newton seconds, or kilogram meters per second. Honestly, you can switch between those units and it doesn't matter. Okay, so that's how much impulse is taking place in whatever time it's occurring in. But the part B now is going to tell us what that time is. Okay, so the contact time between the bat and the ball is 1.6 times 10 to the negative 3 seconds. Very short. What is the average force applied by the bat? So it asks us for average force because the nature of hitting a baseball is that it's going to compress while you're hitting it. So if ever you watch hitting a baseball in slow motion, look it up on YouTube, I'm sure you can find it, you'll see that the baseball compresses over time, and so the force the bat is applying is not always uniform. So we have to go with average force. Okay, so the contact between the bat and the ball is that. So we're going to use now impulse equals force times change in time. We already know the impulse, we already know the change in time, so we need to solve for force. So force is going to be impulse divided by time. So that average force is going to be 14.4 Newton seconds divided by 1.6 times 10 to the negative 3 seconds. So your force, the average force being applied to this ball, is going to be 9,000 newtons. That's positive 9,000 newtons, which means it's being applied toward the east. But because the ball started out moving west and ended up moving east, we know that the change happened toward the east, and so it makes sense that the force also was applied toward the east. Example 2. During a downpour, rain falls at 15 meters per second down and hits the roof of a car. The mass of the rain is 0.6 kilograms per second. Find the force exerted on the car by the rain. Now this is a weird question because mass is usually not measured in kilograms per second, but what this question is really asking you to figure out is what's the force exerted on the car by 1 second worth of rain. Okay, so we're not going to calculate force in newtons per second. We're just going to calculate it in newtons, but we're going to assume we're talking about 1 second here. So this is the mass, but we're going to talk about 1 second worth of rain. Okay, so 0.6 kilograms per second, we're really saying that the mass of the rain is 0.6 kilograms and the change in time is 1 second. So that little piece of information actually gives us two things. Okay, we also know that the rain is falling at 15 meters per second down. And when it hits the roof of the car, it slows down to 0. Okay, so we're going to try to figure out the force exerted on the car. So we're going to start off with force times change in time to get the force equals the change in momentum. Because this gives us the mass of the rain and the time it takes to slow down to 0, or really that's just the amount of rain, we can use the change in momentum to figure out how much force is required to take that much rain and slow it down to 0. V2 minus V1. Okay, so we're doing force times 1 second is equal to 0.6 kilograms times 0, V2 is 0 because it's slowing down to nothing, minus 15 meters per second. Okay, now at this point I need to tell you that this question is really no good because this time is not really talking about how much rain we're talking about. This time is supposed to be how much time it takes to slow down to 0, right? So this time right over here, this is supposed to be the time it takes to start at 15 meters per second and end at 0 meters per second. But each raindrop is not taking a full second, or even this whole 0.6 kilograms of rain is not taking a full second to slow down to 0. So it's not a great question, but let's just ignore that for a second and just use what we're given here to figure out what would be the force required to take that much rain, 0.6 kilograms, and slow it down from 15 meters per second to 0 in 1 second. Okay, now when you solve for the force, we're just going to 0.6 times negative 15 divided by 1, you end up with the force is equal to negative 9 newtons. And this is strange. We need to start looking at directions here. The 15 meters per second that I put in there, I made it positive, right? If you notice over here, V2 minus V1, V2 minus V1 is 0 minus 15. So I said that V1 is positive 15, which means that down is positive. That's fine. There's no problem with that. But our final answer here is negative 9 newtons, which would mean up, right? So this is saying that the force exerted on the car by the rain is 9 newtons up. So why does the rain not lift the car? Like, we know that doesn't happen. In this case, the subject of this change in momentum is the rain, not the car. The 0.6 kilograms over here is the mass of the rain. The 15 meters per second and the 0 meters per second, those are all about the rain, not the car. So this negative 9 newtons is actually the force exerted on the rain. But the question is asking us how much force was exerted on the car by the rain. But we know that by Newton's third law, for every action force, there's an equal and opposite reaction force. Oh, that W got big. Newton's third law. We know that whatever force is exerted on the rain is also being exerted on the car, just in the opposite direction. So then the force on the car is also 9 newtons, just down instead of up. So the force on the car force on the car also equals 9 newtons, but down.